Right now, a telescope floating 1 million miles from Earth is rewriting everything we thought we knew about reality. It just confirmed a galaxy that existed when the universe was barely 280 million years old. It should not have been there. Over the next 2 hours, we are going to travel from the edge of the observable universe to the strangest planets ever found, through voids so empty they could swallow entire civilizations. If you enjoy this journey, a like and subscribe means a lot. Take a breath. We begin now. 1 million miles from Earth, there is a machine staring into the past. It does not predict the future. It literally watches history happen. The James Webb Space Telescope sits at a point in space where the gravity of Earth and our star balance out perfectly. It never orbits our planet. It orbits alongside it, always facing the cold, dark, always watching. And what it sees is not the universe as it exists right now. It sees the universe as it was billions of years ago. That is the first thing that changes everything. Light travels fast, roughly 186,000 miles every single second. A beam of light could circle Earth more than 7 times in the time it takes you to blink. But space is so impossibly vast that even at that speed, light from distant objects takes years, centuries, millions of years, even billions of years to reach us. When Webb points its golden mirror at a galaxy 10 billion light-years away, it is not seeing that galaxy today. It is seeing that galaxy as it looked 10 billion years ago. The light just arrived. The image is ancient. Think of it like opening a letter that was mailed before humans existed. The message is real. The sender might already be gone. Every photograph Webb takes is a time machine image, and the farther it looks, the deeper into history it travels. Webb was built specifically for this. Its primary mirror stretches over 21 feet across, made of 18 hexagonal segments coated in a layer of gold thinner than a human hair. Gold reflects infrared light better than anything else, and infrared is exactly what Webb needs. Because here is the catch. The oldest light in the universe has been traveling so long that it has stretched. The expansion of space itself pulls the wavelength longer and longer as it crosses billions of light years. Visible light becomes infrared. It becomes invisible to human eyes and to telescopes like Hubble. Webb was designed to catch exactly that invisible glow. Behind the mirror sits a shield the size of a tennis court. 5 layers of a material thinner than a strand of hair block radiation from our star, from Earth, and from the Moon. Behind that shield, the instruments cool to nearly negative 370 degrees Fahrenheit. That is colder than any natural place in our entire planetary system. The instruments have to be that cold because they are hunting for the faintest heat signatures in the cosmos. Even a trace of warmth from the telescope itself would blind them. Hubble could see back roughly 13 billion years. That was extraordinary. But Hubble was limited to visible and ultraviolet light. Webb goes further. It captures light from over 13.4 billion years ago. That puts it within a few 100 million years of the Big Bang itself. To put that into perspective, the universe is roughly 13.8 billion years old. Webb is looking at light from when the universe was barely a toddler. But what surprised scientists most was not just how far Webb could see. It was what it found when it looked there. The expectation was simple. The further back in time you go, the younger the universe, the fewer galaxies, the dimmer the light. Everything should have looked small, faint, and scattered. Instead, Webb found the opposite. Galaxies that should not have existed yet. Light that was far too bright. Structures that had no business forming that early. In its very first deep field images, Webb captured thousands of galaxies in a single frame, crammed into a patch of sky no bigger than a grain of sand held at arm's length. Every dot in that image is not a star. It is an entire galaxy. Hundreds of billions of stars in each one, packed into a sliver of the sky so small you could cover it with your fingertip. and one of those tiny dots turned out to be the most distant object humanity has ever confirmed. What it revealed shattered predictions across the board. Among the thousands of ancient galaxies in Webb's field of view, one stood out, not because it was the brightest or the largest, because it was impossibly far away. Scientists have now confirmed that a galaxy they call MOMZ14 existed just 280 million years after the Big Bang. That makes it the most distant galaxy ever verified by any telescope in human history. 280 million years sounds like a long time. It is not. The universe is nearly 14 billion years old. If you squeezed all of cosmic history into a single calendar year, this galaxy appeared around January 3rd. The fireworks of creation had barely faded. The champagne had not even gone flat. The universe was still mostly dark, still filled with a thick fog of neutral hydrogen gas that blocked almost all light. Stars had just begun to flicker on for the very first time. And somehow, inside that fog, this galaxy had already formed, already lit up, already started producing heavy elements that should have taken much longer to appear. It was not supposed to be there, and it certainly was not supposed to be that bright. The team that found it used Webb's near-infrared camera. They scanned a region of deep sky over multiple exposures, stacking the data to pull out signals that would otherwise vanish in the noise. When they isolated MOMZ14, they could hardly believe the numbers. The galaxy sits at what astronomers call a redshift of 14.44. Redshift measures how much light has been stretched by the expansion of space. The higher the number, the further back in time the object exists. A redshift above 14 is staggering. It places MOMZ14 in a window that most models said would be almost completely empty, and it was not faint. That was the shock. It was 100 times brighter than theoretical models predicted for galaxies at that age. Compact, luminous, and chemically enriched in ways that should have taken hundreds of millions of additional years. Among the chemicals detected was nitrogen. On Earth, nitrogen makes up most of our atmosphere. In the early universe, it forms only after massive stars have lived, burned through their fuel, and exploded, scattering heavy elements into the surrounding gas. For nitrogen to show up in a galaxy this young means those massive stars formed and died in an incredibly short time, faster than any model had ever suggested. This was not a quiet, primitive collection of the first dim stars. This was a galaxy that had already been through multiple generations of stellar life and death in 280 million years. Scientists compared that to watching a baby stand up, walk, and run a marathon before its first birthday. Something in the early universe was working overtime. Some engine of creation was running hotter and faster than physics had predicted. The research team at the Massachusetts Institute of Technology put it plainly. What Webb sees in the early universe looks nothing like what they predicted. There is a growing gap between what the theories say should be there and what the telescope actually finds, and MOMZ14 is just the beginning. It is also not alone. Over the past 2 years, Webb has identified dozens of galaxies in this impossibly early window that are far brighter and more mature than expected. Some contain active black holes already feeding on surrounding material. Some have already cleared the primordial hydrogen fog around them, punching holes in the dense curtain that filled the early cosmos. What this means is that the universe woke up faster than we thought. The processes that build stars, forge heavy elements, grow black holes, and clear out gas all kicked into gear earlier and harder than our best physics could predict. Every new confirmation pushes the mystery deeper, and just when scientists thought MOMZ14 had pushed them far enough, a new survey revealed something even harder to explain. Not one anomaly, not a dozen, 300 of them, all at once. Finding one galaxy that is too bright for its age could be a fluke. Finding 10 might be a pattern. Finding 300 forces you to throw out the textbook. A team at the University of Missouri aimed Webb's infrared cameras at the deepest regions of the observable universe and used a technique called dropout analysis. The idea is elegant. When you photograph the same patch of sky through different color filters, the most distant galaxies will appear in the reddest filters and vanish completely in the bluer ones. That sudden disappearance, or dropout, tells you the object is so far away that the expansion of space has shifted all of its light beyond visible wavelengths. By tracking which filters a galaxy drops out of, you can estimate its distance and age. Using this method, the team found 300 objects that were far brighter than any model allows for galaxies that old. Some of these candidates appear to date back to the first few 100 million years of cosmic time. At that stage, the universe should have barely started assembling its first stars. There should not be enough time for galaxies to grow large, produce heavy elements, and emit that much energy. The researchers were careful. They acknowledged that not all 300 are guaranteed to be real early galaxies. Some might be closer objects that mimic the dropout signature. But even if only a fraction are confirmed, the implications are enormous. One of them has already been verified using spectroscopy, the gold standard for confirming a galaxy's true distance. Spectroscopy splits light into its component wavelengths, like a prism turning white light into a rainbow. Each element leaves a unique fingerprint in that rainbow, and the position of those fingerprints tells you exactly how much the light has been stretched by cosmic expansion. That single confirmed object shows this is not a glitch. Something real and unexplained is happening in the early universe. The lead scientist said it bluntly. Even if only a few of these objects are confirmed to be in the early universe, existing theories of galaxy formation will need to be modified. So what could explain this? Scientists have a few ideas, and none of them are comfortable. One possibility is that the first generation of stars were far more massive and far more luminous than anything we see today. These hypothetical giants, sometimes called population 3 stars, could have burned through their fuel in just a few million years, flooding the surrounding space with enough ultraviolet radiation to light up entire regions of gas. If the early universe was filled with these megastars, it would explain the extra brightness. The problem is that nobody has ever directly observed one. They remain theoretical. Another possibility is that black holes in the early universe were growing much faster than anyone imagined. If supermassive black holes formed from the direct collapse of enormous gas clouds rather than from the slow growth of stellar remnants, they could have started big and gotten bigger at a ferocious rate, pouring out energy as they consumed matter. That energy would make their host galaxies appear far brighter than a galaxy powered by stars alone. A third idea is wilder. Maybe the rules we use to calculate how fast galaxies can form are simply wrong. Maybe the relationship between dark matter, ordinary matter, and gravity in the early universe worked differently than the models assume. If dark matter clumped together faster than expected, it could have dragged gas into dense pockets sooner, kickstarting the whole process ahead of schedule. Whatever the answer is, it will change something fundamental about how we understand the first chapter of cosmic history. 300 bright, unexplained objects sitting in a region of time that was supposed to be nearly empty. And to understand why this matters, you need to picture what the universe actually looked like during those first few 100 million years. It was nothing like today. Close your eyes and try to imagine total darkness. Not the darkness of night, where you can still see stars if you look up. Not the darkness of a room, where light creeps under the door. Imagine a darkness so complete that photons, the particles that make up light, cannot travel more than a short distance before being absorbed. That is the early universe. After the Big Bang, everything was unimaginably hot and dense. Energy and matter were tangled together in a screaming chaos of particles that could not form atoms, could not form molecules, could not do anything except collide and scatter. As space expanded and temperatures dropped, protons and electrons finally slowed down enough to combine into the simplest atoms: hydrogen, helium, tiny amounts of lithium. That was all. This moment, roughly 380,000 years after the Big Bang, released a flash of light that still exists today. We call it the cosmic microwave background. It fills the entire sky in every direction and represents the oldest light in existence. After that flash, the universe went quiet. What followed is sometimes called the cosmic dark ages. There were no stars, there were no galaxies, just enormous clouds of neutral hydrogen and helium drifting in expanding darkness. Gravity had started pulling some of this gas together, but slowly. The densest regions attracted more gas over millions of years, growing heavier and heavier until the pressure at their centers became extreme enough to ignite nuclear fusion. The very first stars sparked to life. Nobody knows exactly when the first star ignited. Estimates place it somewhere between 100 million and 250 million years after the Big Bang. Webb is pushing toward that window, but it has not reached it yet. What it has found are galaxies that already contain mature stars, heavy elements, and active black holes at ages that overlap with that window, meaning the transition from total darkness to cosmic light happened faster and more violently than anyone modeled. Those first stars lived fast and died hard. If they were the supermassive populationed three giants that theorists predict, they would have been hundreds of times heavier than anything burning in the sky today. Their cores would have fused hydrogen into helium, helium into carbon, carbon into oxygen, and heavier elements all the way up the periodic table in a matter of a few million years. When they finally collapsed and exploded, they seeded the surrounding gas with the raw ingredients for planets, water, and eventually life. Each explosion did something else as well. The blast of ultraviolet radiation from these dying stars began to ionize the neutral hydrogen around them. Ionizing means stripping electrons off atoms, turning opaque gas transparent. Light could finally travel through the cleared zones. Imagine standing in a thick fog and watching circles of clarity burn open around distant bonfires. That is what was happening across the universe. Scientists call this the epoch of reionization. Webb has confirmed that some galaxies at extremely high redshift appear to have already cleared the hydrogen fog in their surrounding neighborhoods. MOME Z14, the record holder from Chapter 2, is one of them. For a galaxy that young to have already punched through the fog means it was producing extreme amounts of radiation. That alone is a challenge to the standard timeline. The epoch of reionization probably did not happen all at once. It likely took hundreds of millions of years, with bubbles of clear space growing and merging until the entire universe became transparent. By around 1 billion years after the Big Bang, most of the fog had cleared. Light could finally travel freely across cosmic distances. The universe we recognize, full of stars and galaxies and open space, had begun to take shape. But at the heart of many of those earliest galaxies, something massive and hungry was already growing, and Webb caught it in the act. Here is a problem that keeps astrophysicists awake. Some of the earliest galaxies Webb has observed contain supermassive black holes. These are not small objects. They weigh hundreds of millions, sometimes billions of times more than our own star, and they already existed less than 1 billion years after the Big Bang. That should not work. Under the standard model, black holes begin as the remnants of dead stars. A massive star collapses, forms a stellar black hole weighing maybe 10 or 20 times the mass of our star, and then slowly grows by swallowing gas and smaller objects. The problem is the word slowly. There is a speed limit to how fast a black hole can eat. As matter falls toward a black hole, it heats up and generates outward pressure from radiation. That pressure pushes back against incoming material. Physicists call this the Eddington limit. It sets a ceiling on how fast a black hole can grow through normal feeding. If you start with a small, stellar black hole and let it eat at the Eddington limit non-stop for 1 billion years, you end up with something far smaller than the monsters Webb has detected. The math does not add up. You cannot grow a 1 billion mass black hole in less than 1 billion years starting from a 20 mass seed, not unless something unusual happened. Webb has now confirmed an actively growing supermassive black hole inside a galaxy that existed just 570 million years after the Big Bang. The galaxy belongs to a strange class of objects that has baffled astronomers. These objects are compact, luminous, and red, and they have earned the nickname Little Red Dots. Hundreds of them now appear in Webb's deep field surveys, scattered across the early universe like unexpected sparks in the dark. The confirmed black hole in this particular galaxy represents a vital clue. It tells scientists that supermassive black holes were not rare exceptions in the early universe. They were common, and if they were common, then the process that made them must be fundamentally different from anything we see today. One leading theory is called direct collapse. Instead of starting small and growing slowly, some black holes may have been born big. In the early universe, conditions were extreme. Massive clouds of pristine hydrogen gas, never contaminated by metals from dead stars, could have collapsed directly into black holes weighing tens of thousands or even hundreds of thousands of star masses. These seed black holes started the race with a massive head start. From there, they only needed to eat at moderate rates for a few 100 million years to reach the billion-mass range Webb is detecting. A team led by astrophysicist Priyamvada Natarajan predicted this scenario over a decade ago. She described what the signature of such an event would look like: a galaxy whose light is dominated not by stars, but by a black hole growing at its center. The little red dots match that description disturbingly well. Another possibility involves mergers. If smaller black holes frequently collided and fused in the dense early universe, they could have combined their masses rapidly, skipping ahead of the Eddington limit entirely. Gravitational wave detectors have already confirmed that black hole mergers happen. Whether they happened often enough and early enough to explain the Webb observations is still an open question. In one survey, Webb found that 8 quasars in the young universe contained black holes ranging from 600 million to 2 billion times the mass of our star. All of them existed less than a billion years after the Big Bang. Some of those quasars are driving enormous winds that extend across entire galaxies, pushing gas outward and altering the course of galaxy evolution. Whatever built these early monsters, they shaped the universe around them in ways we are only beginning to trace. But some of the strangest objects in Webb's catalogue are not supermassive black holes at all, or at least, nobody is sure what they are. They showed up in nearly every deep survey: small, compact, impossibly red, and impossibly bright. The James Webb Space Telescope kept finding them in the most distant corners of the universe, scattered across images like tiny drops of blood on a dark canvas. Scientists gave them a straightforward name, little red dots, but there is nothing simple about what they actually are. At first, many researchers assumed they were small, extremely dusty galaxies. Red color in astronomy often means dust. Particles of carbon and silicon scatter shorter wavelengths and let longer, redder light pass through. An early galaxy choked in dust would look red. That explanation was tidy. It fit existing models. But as more data came in, the tidy explanation started to fall apart. The little red dots were too compact. Normal galaxies at that distance, even dusty ones, should appear somewhat extended across the image. These objects were point-like, nearly unresolved, even with Webb's extraordinary sharpness. That level of compactness is more consistent with a single, powerful source of light than with a spread-out collection of stars. Then came the spectroscopy. When scientists broke the light from several little red dots into its component wavelengths, they found emission lines associated with gas moving at extreme velocities. Gas that fast usually orbits something enormously massive and compact. The signatures looked more like the environment around an active black hole than like a normal star-forming galaxy. That discovery opened a strange door. Some of these objects might not be galaxies at all. They might be something new. One idea gaining traction is that the little red dots are overmassive black holes sitting at the centers of tiny, faint galaxies. In this scenario, the light we see is almost entirely from the black hole's feeding process, not from stars. The galaxy is there, but it is so dim compared to the black hole that it practically disappears. Imagine a lighthouse sitting on a tiny island. From a distance, all you see is the light. The island is invisible. A team using Webb data from late 2025 made a breakthrough with one of these objects. They performed what is called a dynamical mass measurement on a little red dot at high redshift. By tracking how gas moves around the central object, they estimated its mass at roughly 50 million times that of our star. For a galaxy at that point in cosmic history, a central black hole that heavy is far too large relative to the number of stars around it. It is overmassive. It challenges the relationship between black holes and galaxies that holds true everywhere in the nearby universe. In the modern cosmos, black holes and their host galaxies grow together in a balanced ratio. A galaxy with a certain number of stars tends to have a black hole of a predictable mass at its center. The little red dots break that rule completely. Their black holes are too big for their galaxies, suggesting that in the early universe, black holes may have grown first, and the galaxies built up around them later. That flips the usual order of events. And there is another wrinkle. Some researchers now argue that a subset of the little red dots might not be powered by black holes either. Instead, they could be a completely unknown type of astronomical object, something dense, compact, and luminous that does not fit any existing category. That possibility is still speculative, but the data has not ruled it out. The mystery matters because these objects are everywhere in Webb's early universe images. They are not rare curiosities. Whatever they are, they played a major role in the first billion years of cosmic history. Understanding them could rewrite the entire story of how galaxies and black holes came to exist. And it turns out that the key to solving this puzzle might not be in the objects themselves. It might be in the invisible substance that controls where everything in the universe forms in the first place. Everything you have ever seen, touched, or measured makes up roughly 5% of the universe. Every star, every planet, every atom in your body, every drop of water in every ocean, all of it is 5%, the rest is invisible, and most of that invisible majority is something called dark matter. Dark matter does not glow. It does not absorb light. It does not interact with electromagnetic radiation in any way we can detect. You cannot see it, photograph it, or touch it. If you could hold a chunk of dark matter in your hand, it would pass straight through your palm and fall through the floor and keep falling through the earth itself. It does not interact with normal matter except through gravity, but it is there. Scientists know this because of what it does to the things they can see. Galaxies spin faster than they should. Galaxy clusters hold together when they should fly apart. Light bends around regions of space that appear to contain nothing visible. Something massive is pulling, warping, and shaping the universe. And dark matter is the only explanation that fits all the evidence. It makes up roughly 27% of everything that exists. Dark energy, an even stranger force that accelerates the expansion of space, accounts for the remaining 68%. Together, the visible universe you and I experience is a thin sprinkle on top of an enormous invisible foundation. For decades, scientists have mapped dark matter indirectly by studying how its gravity bends light from distant galaxies. This technique, called gravitational lensing, works because mass curves space. When light from a faraway galaxy passes near a large clump of dark matter, the path of that light bends. The galaxy behind it appears distorted, stretched, or even duplicated. By measuring the distortion, scientists can calculate how much dark matter sits between us and the distant light source. Webb has now produced the most detailed dark matter map ever created. Using observations from a survey field that has been studied for years, scientists combined Webb's infrared data with gravitational lensing analysis to trace the invisible scaffolding of the cosmos with new precision. The resulting map confirms what earlier studies suggested, but with finer detail than ever before. Dark matter did not stay spread out evenly after the Big Bang. It began clumping together first. Gravity pulled it into dense regions, which then attracted normal matter. Gas flowed along the rivers of dark matter, pooling where the dark matter was thickest. Those dense pools became the birthplaces of stars and galaxies. The new map shows this process clearly. Wherever dark matter is concentrated, galaxies cluster together in bright, dense communities. Wherever dark matter thins out, space is barren and cold. The entire arrangement of the visible universe, every galaxy cluster, every filament, every void, follows the invisible pattern laid down by dark matter billions of years ago. Think of dark matter as the skeleton and visible matter as the skin. Without the skeleton, nothing holds its shape. Remove dark matter from the equation, and the entire cosmic structure would collapse into randomness. What makes Webb's contribution special is the depth. Because Webb can see further back in time, it can trace how dark matter has evolved. Early in the universe, the dark matter distribution was smoother. Over billions of years, gravity pulled it into tighter and tighter clumps. The map lets scientists watch that process unfold across cosmic time, comparing the smooth early distribution to the lumpy present-day structure. This matters because the behavior of dark matter controls the large-scale architecture of the entire cosmos. Every galaxy, every cluster, every filament and void owes its position to where dark matter decided to gather. Understanding that process is not optional for astronomers. It is the foundation for understanding everything else Webb discovers. Without dark matter, there is no cosmic web, no galaxies, no stars, and no planets. Nothing we care about would exist. But Webb also found something the map alone could not explain. The shapes of the earliest galaxies look wrong, and the reason might force scientists to reconsider what dark matter actually is. The standard theory says dark matter is cold, not in temperature, but in speed. Cold dark matter particles move slowly compared to the speed of light. They clump into small, dense knots with sharp edges and rough textures. Over billions of years, these clumpy knots merge together, building bigger and bigger structures. This model, called the cold dark matter model, has been the backbone of cosmology for decades. It explains most of the large-scale structure of the universe beautifully. Then Webb looked at the earliest galaxies and found something the cold model struggles to reproduce. Many young galaxies from the first 1 to 2 billion years after the Big Bang appear strikingly elongated, not round, not disc-shaped like familiar spirals, stretched out like beads on a string, or like cosmic sausages embedded in long, thin structures. Scientists had expected some oddly shaped galaxies in the early universe, but the number and degree of elongation caught everyone off guard. Teams at the Massachusetts Institute of Technology, Harvard, and research centers in Taiwan ran simulations to try to match what Webb observed. They fed the standard cold dark matter model into supercomputers and let it build virtual galaxies. The simulated galaxies came out too round, too compact. The cold model could not reproduce the extreme elongation that Webb kept showing. Then they tried something different. They swapped cold dark matter for two alternative versions: warm dark matter and wave dark matter. Warm dark matter particles move faster, which smooths out the smallest clumps and creates softer, more flowing structures. Wave dark matter goes further. It treats dark matter as an ultralight particle that behaves partly like a wave, producing smooth, filamentary patterns at small scales. When they ran the simulations with warm and wave dark matter, the results changed dramatically. Elongated galaxies appeared in abundance. The smoother filaments in these models allowed gas and stars to flow steadily along extended structures, naturally producing the stretched-out shapes that Webb observed. The match was not perfect, but it was far closer than anything the cold model had produced. This result was published in the journal Nature Astronomy, and it sent shockwaves through the physics community. For decades, cold dark matter has been the default assumption. It works well at large scales. It predicts the cosmic microwave background with impressive accuracy. But if the smallest scales, the scales where individual galaxies form, favor a different kind of dark matter, then the entire foundation of cosmological modeling might need revision. To be clear, this is not a confirmed discovery. It is a strong hint. Scientists are calling for more Webb observations, including spectroscopic follow-up, to test whether the elongation trend holds across larger samples. Bigger simulation volumes will also help, but the direction of the evidence is clear. Something about the standard model is not capturing what actually happened in the first billion years. An interdisciplinary scientist on the Webb project described it this way. The earliest galaxies appear to be embedded in smooth filamentary structures that join star-forming regions together, more like what you would expect if dark matter is an ultralight particle with quantum behavior. That sentence contains several ideas that would have been considered fringe just 5 years ago. If dark matter turns out to be warm or wave-like rather than cold, it would affect far more than galaxy shapes. It would influence estimates of how many small galaxies exist, how quickly structures formed, how the universe transitioned from darkness to light, and how the cosmic web, the largest pattern in the universe, assembled itself over billions of years. And that cosmic web is the next piece of the story. Because when you pull back and look at the entire universe at once, you realize that galaxies are not scattered randomly. They follow a pattern so vast and so organized that it took decades for scientists to even recognize it existed, a pattern that connects everything to everything else. Zoom out, keep zooming, past our planet, past the neighboring worlds, past the edge of our star's influence, past the nearest stars, past the galaxy, past the local group of galaxies, past the supercluster, and keep going. At the largest possible scale, the universe reveals a structure so massive that it dwarfs everything inside it. Galaxies are not sprinkled randomly across space. They are organized, arranged along enormous threads, like water droplets, clinging to a spider's web after rain. Scientists call it the cosmic web. It is the single largest pattern in existence, stretching across the entire observable universe and possibly far beyond. The threads of the web are called filaments. These are rivers of dark matter and gas that can stretch for hundreds of millions of light years. Some are thin and delicate. Others are thick and densely packed with galaxies. Galaxies form along them, clustered in the densest regions where filaments intersect. Where multiple filaments meet, you find the biggest structures of all, galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. The coma cluster, containing over 1,000 galaxies crammed into a relatively small volume of space, sits at one of these intersections. Between the filaments, there is almost nothing. Enormous voids, roughly spherical, occupy the space between the threads. These voids can stretch for tens of millions of light years, sometimes hundreds of millions. Inside them, galaxies are rare. Some voids contain only a handful of isolated galaxies drifting through the emptiness. Some appear nearly empty altogether. The voids make up around 80% of the total volume of the observable universe. Think about that. Most of space is empty. The universe you see in photographs, packed with galaxies and nebulae and color, represents a tiny minority of what is actually out there. The structure looks like foam. Imagine the inside of a sponge, magnified to a cosmic scale. The solid parts of the sponge are the filaments and clusters. The holes are the voids. The entire thing is held together by gravity, shaped by dark matter, and constantly evolving as the universe expands. This pattern did not appear overnight. It grew from tiny variations in the density of matter in the very early universe. Right after the Big Bang, matter was spread almost perfectly evenly across space. Almost. There were slight ripples, regions where the density was a fraction of a percent higher or lower than average. Those ripples were imprinted in the cosmic microwave background, and we can still detect them today. Over billions of years, gravity amplified those tiny differences. Regions that started slightly denser attracted more matter. Regions that started slightly less dense lost matter. The dense spots became filaments and clusters. The sparse spots became voids. The structure grew and grew, pulled along by dark matter and fed by rivers of hydrogen gas, until it reached the scale we observe today. What makes the cosmic web particularly remarkable is how it controls the fate of galaxies. A galaxy born inside a dense filament has a very different future than a galaxy born inside a void. Galaxies in filaments interact, merge, steal gas from each other, and form new stars at high rates. Galaxies in voids are isolated. They evolve slowly, quietly, almost undisturbed for billions of years. The environment written into the web at the moment of a galaxy's birth shapes its entire existence. Scientists map the cosmic web using redshift surveys, measuring the distances to millions of galaxies and plotting their three-dimensional positions. The first surveys in the 1980s and 90s revealed the filaments and voids for the first time, confirming what simulations had predicted. Every survey since then has added more detail. But seeing the cosmic web in the early universe, when it was still forming, required something more powerful. It required Webb, and what Webb found was the youngest strand of this web ever detected. 830 million years after the Big Bang, in a region of space so distant that its light has been traveling toward us for over 12 billion years, Webb spotted a line of galaxies, 10 of them, arranged in a thin, diagonal thread stretching 3 million light-years from end to end. It is the earliest cosmic filament ever observed, a fossil from the era when the web was still weaving itself into existence. The discovery came from a project called ASPIRE, which stands for a spectroscopic survey of biased halos. In the reionization era, the program targets 25 quasars from the first billion years of cosmic history. Quasars are galaxies powered by supermassive black holes that consume matter at extreme rates, blazing so brightly they can be seen across the entire observable universe. Each quasar acts like a searchlight, illuminating the gas and galaxies around it. At the center of this particular filament sits one of those quasars. Its black hole anchors the structure, sitting at the densest point of the thread where gravity is strongest. The surrounding galaxies line up along the filament like pearls on a string, tracing the path of the underlying dark matter river that drew them together. The principal investigator of the project, based at the University of Arizona, described how surprised the team was by the length and narrowness of the filament. They expected to find galaxies clustering near the quasar, but they did not expect them to form such a clearly defined, extended line. It looked like a miniature version of the cosmic web filaments seen in the nearby universe, except it existed when the universe was just 6% of its current age. This matters because it tells scientists that the gravitational processes driving the formation of the cosmic web were already well underway within the first billion years. The seeds planted by density ripples after the Big Bang had already grown into recognizable structures. Dark matter filaments had already formed highways for gas and galaxies to flow along. The team also studied the properties of the quasars in their survey and confirmed something remarkable about the black holes at their centers. They range in mass from 600 million to 2 billion times the mass of our star. These monsters were already enormous when the universe was still young, and some of them were driving powerful winds that extended across entire galaxies. One quasar showed evidence of a galactic-scale wind that had never been directly observed this early in cosmic history. The wind, driven by the energy pouring out of the black hole, was pushing gas outward from the center of the galaxy at tremendous speed. The outflow extended across the entire galaxy, altering its structure in real time. This matters because those winds can shut down star formation. They blow away the raw material that stars need to form. A galaxy hit by a quasar wind might stop growing entirely. Its star-making factory simply runs out of fuel. So in the earliest filament ever detected, scientists found evidence of creation and destruction happening simultaneously. Galaxies forming along the dark matter highway, while a supermassive black hole at the intersection blasts some of them clean of their star-forming fuel. Construction and demolition in the same cosmic neighborhood, separated by barely anything at all. Computer simulations had predicted that early quasars would be found at the densest intersections of the primordial web. The Aspire data confirms those predictions with real observations for the first time. It also raises new questions about how environments in the early web shaped the first generation of galaxies and black holes. As striking as this 3 million light-year filament is, it is a baby compared to what the cosmic web produces when given billions of years to grow. The threads get longer, much longer, and some of them are doing something nobody expected. If the early thread web discovered was 3 million light-years long, imagine what happens when the web has 13 billion years to evolve. The filaments grow, they merge, they stretch across distances so vast that the numbers lose all human meaning. The largest known cosmic filaments extend for hundreds of millions of light years. Some reach over 1 billion. At that scale, even galaxies, each containing hundreds of billions of stars, become tiny dots within the thread. Imagine a rope stretching from one end of a football field to the other. Now imagine that each grain of dust on that rope is an entire galaxy. That is closer to the reality, but still not quite large enough. The first filament was confirmed in 1989. In 1996, the idea of a full cosmic web was formally proposed, describing an intricate network of filaments connecting galaxies and superclusters across the observable universe. Since then, survey after survey has filled in the map. The Sloan Great Wall, discovered in 2003, stretches roughly 1.4 billion light-years. For years, it was considered the largest known structure. Then came the Hercules Corona Borealis Great Wall, identified in 2013 from gamma-ray burst data. It extends roughly 10 billion light-years. That is so large it challenges the cosmological principle, the foundational assumption that on the largest scales, the universe looks roughly the same in every direction. A structure that stretches across 7% of the observable universe is difficult to reconcile with a universe that is supposed to be uniform. The filaments themselves are not solid walls of matter. They are more like rivers of dark matter with galaxies clinging to them. The densest parts might contain hundreds of galaxies per volume, while the edges thin out into near-empty transition zones before giving way to voids. Think of a river seen from above. The center is deep and fast. The banks are shallow, and beyond the banks is dry land. A cosmic filament works the same way, except the river is made of invisible dark matter, and the water flowing through it is hydrogen gas feeding galaxies along the way. A recent detection by an international team used Webb and ground-based telescopes to confirm a cosmic filament that is 850,000 light-years long and dates back nearly 12 billion years. That filament spans 9 times the diameter of our own galaxy. It was discovered in a region of sky where nobody expected to find such a large, well-defined structure at that distance. These structures are so diffuse that they are incredibly hard to detect. In the modern universe, filaments contain between 1 and 100 particles per cubic meter. To put that in context, the air you breathe holds roughly 10 trillion molecules in the same volume. The filaments are real, but they are almost unimaginably thin and faint. Detecting them requires either powerful gravitational lensing analysis or telescopes sensitive enough to pick up the faint glow of hydrogen gas flowing along the thread. Webb is uniquely suited for this work in the early universe, because its infrared sensitivity can detect the warm hydrogen that traces the filaments. Ground-based surveys using redshift measurements have mapped the nearby web in remarkable detail. Combining both approaches is giving scientists a 4-dimensional picture, 3 dimensions of space, and 1 of time. They can now compare the web structure at different epochs. watching how it tightened and sharpened over billions of years. The significance goes beyond mapping. The filaments are not just passive structures, they are highways. Matter flows along them. Gas streams toward the intersections where galaxy clusters form. Smaller galaxies fall along the threads, drawn toward the densest regions. Even angular momentum, the spin of galaxies, appears to be influenced by the orientation and flow of the filaments they inhabit. And that brings us to perhaps the most astonishing recent discovery about the cosmic web. A filament 50 million light-years long, containing hundreds of galaxies, and the whole thing is spinning. Every galaxy inside it, rotating together. Galaxies spin, that is well known. The Milky Way rotates once roughly every 230 million years. Spiral arms sweep through star-forming regions. Disks of gas and dust swirl around central bulges. Rotation is fundamental to how galaxies work. But a filament, an entire structure 50 million light-years long, containing more than 280 galaxies, rotating as a single entity, that is something different. That is something that was only just confirmed, and it challenges assumptions about how rotation works at the largest scales. A research team, led by scientists at the University of Oxford, identified a thin string of 14 gas-rich galaxies embedded inside a much larger cosmic filament, roughly 140 million light-years from Earth. The string stretches about 5.5 million light-years long and just 117,000 light-years wide. The galaxies within it are rich in hydrogen, the raw fuel for star formation, and many of them are spinning in the same direction. That alignment is significant. If each galaxy's spin were random, you would expect roughly half to spin one way and half the other. Instead, a disproportionate number align with each other, and with the filament itself, far more than chance would predict. The team compared the observed pattern to random simulations and found the alignment was statistically striking. Even more surprising, the galaxies on opposite sides of the filament's central spine are moving in opposite directions. One side approaches us, the other side recedes. This is the classic signature of rotation. The entire filament appears to be turning, slowly, like a skewer rolling between two hands. Using models of filament dynamics, the team estimated the rotation speed at around 110 kilometers per second. They also estimated the radius of the densest central region at about 163,000 light-years. The picture that emerges is of a rotating cylinder of dark matter and gas, with galaxies riding along its length like passengers on a carousel. One of the lead researchers described it with a vivid comparison. Imagine a teacup ride at a theme park. Each galaxy is like a spinning teacup, but the platform they sit on, the filament itself, is also spinning. Dual motion at two entirely different scales. The filament appears to be young and relatively undisturbed. Its galaxies have low internal velocities, a condition scientists call dynamically cold. This suggests it is still in an early stage of development. The large amount of hydrogen gas in its galaxies supports this. These galaxies are still actively gathering fuel for star formation, drawing it in from the filament around them. This discovery has implications beyond a single structure. If one filament rotates, others might too. And if large-scale rotation is common in filaments, it means the cosmic web itself carries angular momentum on scales previously thought to be rotation-free. Current cosmological models generally do not predict significant rotation in filaments. They predict that matter falls toward dense nodes along straight or gently curved paths, without the kind of organized spin this observation shows. Finding rotation at this scale could provide new insights into how galaxies gain their spin in the first place. If a galaxy inherits part of its angular momentum from the filament it was born in, that would connect the smallest rotational features of galaxies to the largest structures in the cosmos. It would be a thread of cause and effect spanning from cosmic web to spiral arm. The observation could also affect upcoming cosmological surveys. Projects like the Euclid mission and the Vera Rubin Observatory in Chile are designed to study the shapes and orientations of millions of galaxies to probe dark energy. If filament rotation systematically aligns galaxies, it could introduce a bias that these surveys need to account for. Between the filaments, though, lies a very different kind of space. Vast, dark, and almost completely empty. The voids that make up 80% of the universe hold mysteries of their own, and one of them is so enormous that it earned a name, the Great Nothing. Imagine traveling through space for 300 million light-years in a straight line and encountering almost nothing. No galaxies, no clusters, no filaments, just the thinnest possible scattering of hydrogen gas and the cold background glow of ancient radiation. That is what a cosmic void feels like. Voids are the forgotten majority of the universe. While galaxies and clusters get all the attention, the spaces between them are overwhelmingly larger. Roughly 80% of the volume of the observable universe is void. Most of space, in the most literal sense, is empty. Typical voids range from about 30 to 300 million light-years across. They are roughly spherical, though not perfectly so. Their edges blend into the surrounding filaments gradually, with galaxy density increasing as you move outward from the center toward the Webb. At the deepest center of a void, galaxy density drops to near zero. The few galaxies that exist inside voids tend to be isolated, gas-rich, and slowly evolving, untouched by the violent interactions that shape galaxies in dense environments. Scientists first recognized voids in the 1980s when redshift surveys began mapping the three-dimensional positions of galaxies. The surveys revealed a pattern that nobody had predicted in such dramatic detail. Galaxies were not distributed evenly. They clustered along filaments and walls, leaving enormous empty regions between them. The universe looked like soap foam, dense bubbles of galaxies surrounding vast, hollow interiors. The existence of voids is actually a natural prediction of the standard cosmological model. After the Big Bang, tiny density fluctuations seeded the growth of structure. Overdense regions attracted matter and grew into filaments and clusters. Underdense regions lost matter and expanded, becoming progressively emptier as the universe evolved. Gravity pulled material out of the voids and deposited it onto the Webb. Over 13 billion years, this process hollowed out the voids we see today. But here is what makes voids more than just empty patches. They are cosmological laboratories. Because voids are the most underdense regions of the universe, they are the places where dark energy has the strongest relative effect. Dark energy is the mysterious force driving the accelerating expansion of space. In dense regions, gravity partially resists this expansion. In voids, there is almost no matter to resist it. The expansion runs freely. Studying how voids grow and evolve over time gives scientists a direct window into the behavior of dark energy. Voids also carry information about the initial conditions of the universe. Their sizes, shapes, and distributions are sensitive to the properties of dark matter and the physics of the early universe. By comparing observed void statistics to predictions from simulations, scientists can test cosmological models with a precision that complements galaxy-based measurements. Some voids are remarkable for their sheer size. The Eridanus supervoid, discovered in 2007, coincides with an unexplained cold spot in the cosmic microwave background. The cold spot is a region of the microwave sky that is slightly cooler than its surroundings, and the supervoid may contribute to this anomaly by causing photons to lose energy as they pass through the expanding empty space. However, the void alone is not large enough to fully explain the cold spot, leaving the mystery open. Then there is the KBC void, potentially the largest void ever identified, with a radius of roughly 1 billion light-years. And here is the unsettling part. Our galaxy, along with everything in our local cosmic neighborhood, appears to sit inside it. We may be living in one of the emptiest regions of the universe, and most people have never heard of it. But before we explore that possibility, there is one void so famous it earned its own name: and the story of what it would be like to live inside it is one of the loneliest thought experiments in all of astronomy. In 1981, astronomer Robert Kirshner was conducting a redshift survey, mapping how galaxies are distributed in three-dimensional space. As the data came in, a gap appeared, a region in the direction of the Bootes constellation where galaxy after galaxy simply was not there. The gap kept growing. When the survey was complete, Kirshner and his team stared at a hole in the map that stretched 330 million light-years across. Inside that hole, the universe was nearly empty. It was first called the Great Nothing. Later, it became known as the Bootes Void. To understand its scale, compare it to what we know. The Milky Way stretches about 100,000 light-years across. Our local group of galaxies spans roughly 10 million light-years. Even the Virgo supercluster, one of the largest nearby structures, is smaller in total volume than this single void. The Bootes Void could swallow them all without noticing. After its discovery, astronomers expected further surveys to fill in the gap, revealing faint galaxies hidden in the void that earlier instruments had missed. They found some, but not many. By 1997, after years of follow-up observations with increasingly powerful telescopes, only 60 galaxies had been confirmed inside the void. 60. In a region where standard density predictions suggest there should be roughly 2,000. The European Space Agency described one of those 60 galaxies as perhaps the loneliest galaxy in the universe. Its designation is bland, but its situation is extraordinary. It sits deep inside the void, separated from any neighboring galaxy by distances so vast that light from its nearest companion takes millions of years to arrive. If a civilization lived inside that galaxy, with telescopes as powerful as Hubble, they would not have discovered the existence of other galaxies until the 1960s. For most of their astronomical history, they would have believed their galaxy was the entire universe. One island of stars adrift in an infinite ocean of black, no neighbors, no cosmic web, no sense that anything else existed beyond the edges of their own spiral arms. Their sky would be the loneliest sky imaginable. That thought experiment matters. It shows how profoundly your location in the cosmic web shapes what you can know about reality. We happen to live in a relatively dense neighborhood, surrounded by galaxies in every direction. That is why we discovered the large-scale structure of the universe as early as we did. A civilization inside the Bootes Void would have a radically different cosmology, built on radically incomplete data. The void itself is roughly spherical, which is unusual. Most voids in the cosmic web are irregularly shaped, squeezed, and distorted by the surrounding filaments. The Bootes Void is remarkably round. One explanation is that it formed from several smaller voids that merged over time, their combined expansion smoothing the boundaries into a sphere. Simulations support this idea, showing that void mergers can produce large, round structures over billions of years. Does the existence of such a vast, empty region threaten our understanding of the Big Bang? Not necessarily. The standard model allows for statistical variation in the distribution of matter. Some regions will be denser, some will be emptier. The Bootes Void is an extreme case, but it falls within the range of what the model can produce. It is unusual, not impossible. Still, its extreme emptiness raises questions. Why so few galaxies? Why so round? And could there be even larger voids hiding in regions of the universe we have not yet surveyed in detail? Webb's deep field observations, combined with ground-based redshift surveys, may eventually reveal voids that dwarf even the Great Nothing. But we may not need to look far to find one, because some scientists now believe we are already inside a void, right now, and it might be the key to solving one of the biggest disagreements in all of modern physics. This sounds like speculation. It is not. Multiple studies over the past several years have presented evidence that the Milky Way and its surrounding galaxies sit inside a large region of underdensity, a place where there are fewer galaxies per volume than the cosmic average. A void. Scientists call it the KBC void, named after the researchers who characterized it. Its estimated radius is roughly 1 billion light-years. That makes it far larger than the Bootes void. If confirmed at its full extent, it would be one of the largest coherent underdense regions ever identified. The evidence comes from galaxy counts. When astronomers compare the number of galaxies in our local cosmic neighborhood to the number in regions further away, they consistently find that our neighborhood has fewer. The deficit ranges from roughly 15 to 50%, depending on the survey and method used. We are not sitting in a complete desert, but we are in a region noticeably emptier than average. This does not mean our immediate surroundings feel empty. The Milky Way is part of the local group, which contains more than 50 galaxies. The local group sits within the Virgo supercluster. The Virgo supercluster is part of an even larger structure called Laniakea, which contains roughly 100,000 galaxies across 500 million light-years. That sounds plenty dense, but on the scale of billions of light-years, our entire region is underdense compared to the broader universe. And this could matter enormously for physics, because the KBC void might solve one of the most frustrating puzzles in modern cosmology. For over a decade, scientists have been arguing about how fast the universe is expanding. The argument is called the Hubble tension, and it goes like this. If you measure the expansion rate using the cosmic microwave background, the ancient light left over from 380,000 years after the Big Bang, you get a number, roughly 67.4 kilometers per second per megaparsec. If you measure the expansion rate using nearby objects like supernovae and variable stars, objects whose distances can be calibrated directly, you get a different number, roughly 73 kilometers per second per megaparsec. That gap, about 8%, might sound small. It is not. Both measurements have been refined to extraordinary precision. The error bars no longer overlap. Something is wrong. Either one measurement has a systematic flaw nobody has found, or there is new physics hiding in the gap. The KBC void offers a potential escape. If we live inside a large, underdense region, the local expansion rate would naturally appear faster than the global average. Inside a void, there is less gravity to slow the expansion down. Objects near us would appear to recede faster than objects far away. That local speedup would make our nearby measurements come out higher, while measurements based on the cosmic microwave background, which reflect the global average, would come out lower. A physicist at the University of Portsmouth described the logic clearly. The Hubble tension is largely a local phenomenon, with little evidence that the expansion rate disagrees with expectations further back in time. So a local solution, like a local void, is a promising approach. For this explanation to work, the Milky Way would need to sit near the center of the void, and the void would need to be roughly 20% less dense than the universe's average. Current estimates of the KBC void's properties are consistent with these requirements, but more data is needed to confirm the exact density profile and our position within it. If the void explanation holds, it would be a relief in one way and a shock in another. Relief because it would resolve the Hubble tension without requiring exotic new physics. Shock because it would mean the universe, at large scales, is less uniform than the cosmological principle assumes. We would have to accept that our position in the cosmos is not typical. We live in a hole. Whether or not we live in a void, the Hubble tension itself is real, and Webb keeps making it more complicated. 2 numbers. That is all it takes to create a crisis in cosmology. 2 measurements of the same quantity that refuse to agree. The quantity is called the Hubble constant. It describes how fast the universe is expanding at this moment, not how fast it expanded in the past, or how fast it will expand in the future. Right now, the number tells you that for every megaparsec of distance, roughly 3.26 million light-years, galaxies are moving away from each other at a certain speed. The first method to measure it looks backward. The cosmic microwave background, the oldest light in the universe, carries a pattern of temperature fluctuations that encodes the expansion history of the cosmos. By fitting that pattern with a precise mathematical model, scientists can calculate what the Hubble constant should be today. This method gives a value of roughly 67.4 kilometers per second per megaparsec. The data comes primarily from the European Space Agency's Planck satellite, and it has been tested, retested, and confirmed to extraordinary precision. The second method looks nearby. Scientists identify objects whose true brightness is known, a specific type of exploding star called a type Ia supernova, or a type of pulsating star called a Cepheid variable. Because the true brightness is known, the observed brightness tells you the distance. Combining distance with the speed at which the object is moving away from us gives you the expansion rate. This method consistently produces a value around 73 kilometers per second per megaparsec. The team behind this measurement, led for years by Nobel laureate Adam Rees, has checked every possible source of error. The number holds. The tension is in the gap, 6 kilometers per second per megaparsec. It does not sound like much until you realize what it implies. Either the early universe method is missing something, the nearby method is missing something, or the model connecting them is incomplete. That model is the lambda cold dark matter model, the standard framework that describes the composition and evolution of the entire cosmos. If the model is wrong, the consequences ripple across all of physics. Webb has entered this fight because Webb can observe Cepheid variable stars in distant galaxies with better resolution than Hubble ever could. It has been used to recheck the nearby measurements. Early results suggest that the nearby value holds up even with Webb's sharper instruments. The tension is not a calibration error. It appears to be real. Several exotic explanations have been proposed. Maybe dark energy is not constant but changes over time. Maybe there is a new type of particle that slightly altered the expansion rate in the early universe. Maybe the universe went through a brief period of unusual behavior that current models do not account for. The void explanation from the previous chapter is one of the simpler possibilities. Others are far stranger. Some theorists have suggested that the universe might have slightly different expansion rates in different directions, violating the assumption of isotropy. Others propose modifications to general relativity, Einstein's theory of gravity, that would change how expansion is calculated. None of these proposals have been confirmed. The tension remains open, and it remains one of the most important unresolved problems in science. If the answer turns out to be a local void, we learn something humbling about our position in the cosmos. If the answer turns out to be new physics, we learn something that could transform our understanding of everything from dark energy to the fate of the universe. Every year, new observations narrow the possibilities. Webb is playing a central role, but the answer, whatever it is, will not just adjust a number on a page. It will change how we think about the universe we inhabit. And speaking of the universe we inhabit, there is a question that most people get wrong. Just how big is it? Most people hear that the universe is roughly 14 billion years old and assume it must be roughly 14 billion light years across. That makes intuitive sense. If nothing can travel faster than light, and the universe started 14 billion years ago, then the farthest anything could possibly be is 14 billion light years away. That assumption is wrong. The observable universe is 93 billion light years in diameter, and it might keep going far beyond that. The reason is expansion. Space itself is stretching. It has been stretching since the Big Bang. As light from a distant galaxy travels toward us, the space between us and that galaxy continues to grow. By the time the light arrives, the galaxy has moved much further away than it was when it emitted the light. The photon traveled a certain distance, but the destination kept retreating. Think of it this way. Imagine two ants on a rubber band, 3 inches apart. One ant starts walking toward the other, but while it walks, someone stretches the rubber band. By the time the walking ant reaches the spot where the other ant used to be, the rubber band is longer, and the other ant has been carried further away. The walking ant traveled 3 inches, but the gap is now 5. That is what happens with light in an expanding universe. The cosmic microwave background, the oldest light we can detect, was emitted roughly 380,000 years after the Big Bang from a surface that was, at that time, about 42 million light-years from the point that would eventually become our location. That light has been traveling for nearly 14 billion years. But during that journey, space expanded so much that the source of that light is now about 46.5 billion light-years away from us. In every direction, that gives the observable universe a total diameter of roughly 93 billion light-years. And observable is the key word. That is only the part of the universe whose light has had time to reach us. Beyond the observable edge, there is almost certainly more universe, possibly much more. Some models suggest the total universe could be hundreds of times larger than what we can see. Others suggest it might be infinite. We will never know for certain. Light from beyond the observable edge has not had time to reach us, and, due to the accelerating expansion of space, it never will. Those regions are moving away from us, faster than light. That does not violate relativity, because nothing is traveling through space faster than light. Space itself is expanding, carrying distant regions away at speeds that exceed the speed of light when measured across cosmological distances. This means there is a hard limit to what any telescope, no matter how powerful, can ever show us. Webb can push close to the edge of the observable universe. It can photograph galaxies from when the universe was only a few 100 million years old. But there will always be regions beyond our reach, regions that may contain galaxies, stars, and planets we will never see or know about. The sheer scale is difficult to internalize. If you could somehow freeze the expansion and travel at the speed of light, it would take you over 46 billion years to reach the edge of the observable universe in one direction, 93 billion years to cross the whole thing, and the whole thing might be just a tiny fraction of what actually exists. Webb cannot show us everything. No instrument can. But what it has shown us already has forced scientists to reconsider the chemistry and biology of the early cosmos. Because among those impossibly bright early galaxies, Webb found chemical fingerprints that tell a story of creation happening faster than anyone thought possible. Chemistry takes time. Heavy elements do not appear out of nowhere. They are forged inside stars, in the intense heat and pressure of nuclear fusion, then scattered into space when those stars explode. The next generation of stars forms from the enriched debris, and the cycle repeats. Each generation adds more complexity. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, nitrogen, silicon, iron. Every element heavier than helium was built inside a star that is now dead. This process is called nucleosynthesis, and scientists have mapped it in detail. They know which elements form at which stages of a star's life. They know how long each stage takes. They know how many generations of stars it requires to build up a rich chemical environment. And until Webb, they believed this process needed hundreds of millions of years, at minimum, to produce measurable amounts of heavy elements in any galaxy. Webb found those elements in galaxies that should not have had time to make them. The record-breaking galaxy MOMZ-14, confirmed at just 280 million years after the Big Bang, shows elevated levels of nitrogen in its spectrum. Nitrogen is not a simple element to produce. It forms primarily during a specific phase of stellar evolution called the carbon-nitrogen-oxygen cycle, where carbon, nitrogen, and oxygen atoms act as catalysts inside the cores of massive stars. For nitrogen to appear in significant amounts, you need multiple generations of massive stars to live and die, each one contributing its processed material to the gas from which the next generation forms. At 280 million years, there has barely been time for one generation of stars, let alone several. The presence of nitrogen at that age implies that stellar evolution in the early universe happened at a pace that current models cannot easily reproduce. Stars formed faster, burned hotter, died sooner, and recycled their material more efficiently than anything we see in the nearby cosmos. Scientists have looked for an analogy closer to home and found a suggestive clue in our own galaxy. A small percentage of the oldest stars in the Milky Way also show unusually high levels of nitrogen. These ancient stars formed from gas that was enriched very early in cosmic history, and their chemical signatures match what Webb is detecting in distant galaxies. The connection suggests that whatever process created the nitrogen enrichment in the early universe left traces that survived for billions of years, frozen in the atmospheres of the oldest surviving stars. The chemical maturity extends beyond nitrogen. Some early galaxies also show signs of being more compact and more chemically enriched across multiple elements than expected. The gas inside them has already been processed through stellar interiors and recycled. Dust grains, made of heavier elements like silicon and carbon, are already present. These are markers of an evolved system, not a newborn one. One explanation involves stars far more massive than anything currently burning in the universe. If the first generation of stars included monsters weighing several hundred times more than our own star, they would have lived for only a few million years before exploding in catastrophic supernovae. Each explosion would have flooded the surrounding gas with heavy elements far faster than smaller, longer-lived stars could manage. A handful of these megastars could chemically enrich an entire region of space in a fraction of the time the Standard Model predicts. These hypothetical first-generation megastars are called population 3 stars. No telescope has ever directly observed one. They are a theoretical prediction based on the conditions of the early universe: pristine gas, no metals, and extreme densities that favor the formation of very massive objects. Webb's chemical detections are the strongest indirect evidence yet that population 3 stars existed and that they shaped the earliest epoch of star formation. But Webb has not only looked backward in time, it has also turned its instruments toward planets orbiting other stars, and what it found there is just as unsettling. Starting with a world covered entirely in liquid rock. For decades, scientists have asked a single question about rocky planets orbiting other stars. Do any of them have air? Not a thin wisp of hydrogen left over from formation. Real air. A thick, persistent atmosphere clinging to a world of rock and metal, the way ours clings to Earth. Without an atmosphere, a planet is just a dead ball of stone baking in starlight. With one, everything changes. Weather becomes possible. Chemistry becomes possible. And with enough of the right chemistry, life becomes possible. Webb just gave us the first strong answer, and it came from one of the least likely places imaginable. The planet is called TOI 561b. It orbits a star about 280 light-years from Earth. That star is roughly 10 billion years old, twice the age of ours, making it one of the most ancient planetary systems ever studied. The planet itself is a nightmare. It is roughly 1.4 times the size of Earth, about twice its mass, and it completes one full orbit around its star in less than 11 hours. Its year is shorter than a workday. It circles at a distance of less than 1 million miles, which is 1/40th the distance between Mercury and our star. At that range, one side permanently faces the star, locked in endless daylight. The other side never sees light at all. The dayside temperature should be close to 4,900 degrees Fahrenheit. That is hot enough to melt rock. Scientists believe the entire sunlit hemisphere is covered by a global ocean of magma, liquid stone stretching from horizon to horizon, glowing under a sky of vaporized minerals. Everything about this world screams that it should be stripped bare. Radiation from the star should have blasted away any atmosphere long ago. Small planets this close to their host stars have always been assumed to be airless. They are too hot, too irradiated, and too small to hold onto gas. Webb proved that assumption wrong. Using its near-infrared spectrograph, The team measured the temperature of the planet's dayside by watching how the combined brightness of the star and planet changed as the planet moved behind the star. If the planet were a bare rock with no atmosphere, the dayside should have measured close to 4,900 degrees Fahrenheit. Instead, it measured around 3,200 degrees, still brutally hot, but far cooler than expected. The difference tells a story. Something is carrying heat from the dayside to the dark side. Something is absorbing some of the starlight before it reaches the surface. Something is cooling the planet down. The only explanation that fits all the data is a thick, volatile, rich atmosphere. Strong winds would transport heat around the planet. Gases like water vapor would absorb infrared light, lowering the apparent temperature. The atmosphere is not thin, it is substantial. The scientists describe the planet as a wet lava ball. They believe there is an equilibrium between the magma ocean and the atmosphere. Gases constantly escape from the molten surface, feeding the atmosphere from below. At the same time, the magma reabsorbs some of those gases, pulling them back into the interior, a cycle of outgassing and ingassing that keeps the atmosphere alive despite the brutal radiation. This planet is not habitable. Nothing could survive on a world of boiling rock under a sky of metal vapor. But the discovery proves something critical. Rocky planets can hold on to atmospheres in conditions that were thought to make it impossible. If this ancient, scorched world still has air after 10 billion years, then cooler, more temperate rocky worlds almost certainly do too. And if rocky planets with air are more common than we assumed, the search for life in the universe just got a lot more interesting. But before we chase that question, Webb has another planet to show you. One so strange that no known theory can explain how it got there. There is a planet orbiting a dead star that should not exist. It is shaped like a lemon. Its atmosphere is made of carbon and helium, with clouds of soot drifting through the air. Deep inside, the pressure is so extreme that carbon crystals likely form. Those crystals are diamonds, and nobody can figure out how this world came to be. The planet is officially named PSR-J 2000, 322,650b. It orbits a pulsar, a rapidly spinning neutron star that is roughly the mass of our star, but crushed down to the size of a city. About 12 miles across, a tablespoon of neutron star material would weigh as much as a mountain. The planet circles this bizarre object at a distance of about 1 million miles, completing a full orbit in under 8 hours. At that range, the pulsar's intense gravity stretches the planet into an elongated shape, like a football or a lemon, constantly deformed by tidal forces that would rip most objects apart. When Webb's instruments captured the planet's spectrum, the team expected to find the usual mix of molecules: water, methane, carbon dioxide, the standard ingredients of gas giant atmospheres across the galaxy. Instead, they found something entirely different. The atmosphere is dominated by helium and molecular carbon. Specifically, molecules made of 2 and 3 carbon atoms. No water, no methane, no carbon dioxide, just helium and carbon, with dark, soot-like particles floating through the upper layers. The principal investigator, an astrophysicist at the University of Chicago, described the team's reaction in 2 words: absolute surprise. This is a type of planetary atmosphere that nobody has ever seen before. It matches no existing model. It fits no known formation pathway. How do you make a planet with pure carbon in its atmosphere? The standard route is through stellar evolution. Stars produce carbon in their cores through nuclear fusion. But planets do not normally inherit pure carbon atmospheres. They form from disks of gas and dust around young stars, collecting a mix of hydrogen, helium, water, and various other molecules. A planet made almost entirely of helium and carbon suggests a very different origin. One theory involves the pulsar itself. Pulsars are the remnants of massive stars that exploded as supernovae. Before the explosion, the original star may have had a companion. In some binary systems, the pulsar strips material from its partner, slowly consuming it. These are called black widow systems, because the pulsar gradually devours its companion. In this case, the companion was not fully consumed. What remains is a Jupiter mass object, stripped of its outer layers, exposing an interior enriched in carbon and oxygen from the original star's nuclear processing. But even that explanation has problems. Nuclear physics does not produce pure carbon. The stripping process should leave behind a mix of elements, not a clean carbon-helium atmosphere. One researcher proposed that as the companion cooled over time, the mixture of carbon and oxygen in its interior began to crystallize. Pure carbon crystals, being lighter, floated to the top and mixed into the helium atmosphere. The oxygen and nitrogen somehow separated and sank. If true, those floating carbon crystals are diamonds, rising through the interior like ice cubes in a glass of water, reaching the atmosphere and creating the soot clouds that Webb detected. The system offers one unique advantage for study. Because the pulsar is so small and emits almost no visible light, the planet's spectrum is remarkably clean. Scientists can study its atmosphere without the glare of a nearby star contaminating the data. It is one of the purest planetary spectra ever obtained. Yet the fundamental question remains: how did this object form? Every known mechanism has been ruled out. It did not form like a normal planet. It was not created by standard black widow stripping. Something else happened, and nobody knows what. This lemon-shaped world covered in soot and diamonds remains, for now, completely unexplained. And it is not the only exoplanet Webb has caught in the middle of something dramatic. One world is actively tearing itself apart right in front of the telescope. Somewhere in the Milky Way, a planet is dying. Not in the distant future. Right now, it is so close to its star that the surface is vaporizing, shedding material into space with every orbit, leaving behind a trail of debris like a comet screaming through the inner reaches of its planetary system. Webb watched it happen. The planet is a small, rocky world locked in an extremely tight orbit around its host star. The distance is so close that the star's radiation is literally boiling the planet away. Surface material, possibly from the crust, the mantle, or even the core, is being ripped off and carried into space. The Discovery team estimates that the planet loses the equivalent of a Mount Everest's worth of material with every single orbit. Not over millions of years. Every orbit, every few hours, another mountain vanishes into the void. At that rate, the planet will not last. Calculations suggest it could completely disintegrate within 1 to 2 million years. That sounds like a long time, but in astronomical terms, it is an eye blink. The planet is already in its final chapter. Webb happened to catch it at precisely the right moment in cosmic history, during the brief window when it is actively falling apart. The debris forms a tail. As material lifts off the surface, it gets caught in the star's radiation and pushed outward, creating a stream of particles that trails behind the planet like smoke from a burning ember. The composition of that tail is what makes this discovery scientifically priceless. The dust and gas being shed may contain material from deep inside the planet, minerals from the mantle, metals from the core, elements that are normally locked away beneath thousands of miles of rock, completely inaccessible to any telescope. By studying the tail, scientists are getting a rare opportunity to examine the internal composition of a distant world. Normally, that is impossible. You can measure a planet's size. You can measure its mass. You can sometimes detect its atmosphere. But what lies beneath the surface is hidden. This dying planet is cracking itself open and spilling its guts into space, and Webb is there to read the contents. This is the only known case where a rocky planet's deep interior is being exposed in real time. Every observation adds new data about what small, rocky worlds are made of at their cores. That information feeds back into models of planet formation, helping scientists understand how worlds like ours are built. But Webb did not just observe one planet losing material. It turned to a very different kind of world, a massive gas giant called an ultra-hot Jupiter located about 858 light-years from Earth, and found something even more unexpected. This planet is not shedding rock, it is shedding its entire atmosphere. The star's radiation and stellar wind are stripping helium gas from the planet's upper layers and blowing it into space. Webb detected the escaping helium and traced it into two distinct tails. One trails behind the planet, pushed backward by the star's radiation and wind. That was expected. The second tail curves forward, ahead of the planet in its orbit, drawn toward the star by its gravity. A leading tail of this kind is extremely rare and had never been observed with such clarity. The two tails together span nearly 60% of the planet's orbit. Imagine a world dragging two rivers of gas, behind and ahead of it, as it races around its star. The trailing river pushed by light, the leading river pulled by gravity. The planet trapped between two forces, slowly losing itself to both. These observations matter because atmospheric escape determines the long-term fate of close-in planets. If hot Jupiters lose their atmospheres fast enough, they could eventually be stripped down to bare rocky cores. Some scientists believe certain dense, small planets scattered across the galaxy might be the skeletal remains of former gas giants that lost everything. Every dying planet, every escaping atmosphere, every trail of debris is a clue about how planetary systems evolve over billions of years. But the most tantalizing question Webb has chased is not about dying worlds. It is about living ones. 124 light-years from Earth, there is a planet that has ignited one of the fiercest debates in modern astronomy. It is called K218b. It orbits a small red dwarf star in the habitable zone, the region where temperatures could allow liquid water to exist on the surface. It is about 2.5 times the size of Earth and roughly 8.5 times its mass. It is not a rocky world like ours. Scientists classify it as a sub-Neptune, a category of planet that does not exist in our own planetary system, something between a rocky super-Earth and a small gas giant. What makes it extraordinary is what Webb found in its atmosphere. In 2023, a team at the University of Cambridge used Webb's near-infrared instruments to study starlight filtering through the planet's atmosphere as it passed in front of its star. They detected methane and carbon dioxide, both of which are consistent with a hydrogen-rich atmosphere overlaying a water ocean. The combination was striking. On Earth, methane in the presence of carbon dioxide and water is often associated with biological activity. Microorganisms produce methane as a byproduct of their metabolism. But the team also reported something far more provocative, a faint signal consistent with dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine life. Phytoplankton in the oceans release it. It is part of the smell of a sea breeze. If confirmed on K218b, it would be the strongest hint of biological activity ever detected on a world outside our planetary system. The initial detection was weak, barely above the noise. A 2 sigma signal, meaning there was roughly a 5% chance it appeared by random chance. That is far below the 5 sigma threshold that scientists consider definitive. But it was enough to launch a global debate. In April of 2025, the same team published new data from Webb's mid-infrared instrument. They reported that the dimethyl sulfide signal had strengthened to a 3 sigma level, still below the gold standard, but significantly stronger. The researchers argued it was the strongest evidence to date for possible biological activity on an exoplanet. Headlines around the world exploded. Then the pushback began. Multiple independent teams reanalyzed the same data using different methods and reached different conclusions. A NASA-led reanalysis confirmed the presence of methane and carbon dioxide, but found no conclusive evidence for dimethyl sulfide. The team concluded that the signal was too dependent on specific choices in how the data was processed. Change the way you bin the wavelengths, and the signal appears or disappears. Another group went further. They applied the formal astrobiology standards of evidence framework and concluded that K218b does not meet the standards for a life detection. They found that instrumental noise in the mid-infrared data was the more likely explanation for the apparent signal. Nearly 90% of their analyses showed no significant evidence for the molecule. The debate exposed something important about the limits of current technology. Webb was designed before K218b was even discovered. Its instruments are powerful enough to detect the most abundant molecules in an exoplanet's atmosphere, but detecting trace biosignature gases at the parts per billion level pushes it to its absolute limit. The signal, if real, sits right at the edge of what the telescope can reliably measure. Scientists on both sides agree on one thing: more data is needed. Additional Webb observations, using longer exposure times and different instrument modes, could push the detection above or below the threshold. If dimethyl sulfide is confirmed at 5 sigma, it would be the most significant discovery in the history of biology. If it is ruled out, K218b will still remain one of the most important targets for studying potentially habitable atmospheres. For now, the question of life on K218b remains open, tantalizing, unresolved, and a powerful reminder that finding life beyond Earth, if it exists, will not come with a single dramatic announcement. It will come through years of careful measurement, debate, and verification. And the reason this search matters so much is a number so large it changes how you think about the galaxy. Rocky planets are not rare. They are everywhere. Current estimates suggest that tens of billions of rocky planets exist in our galaxy alone, not across the entire universe, just in the Milky Way. The number is so large that it transforms the question of life from a philosophical curiosity into a statistical inevitability that demands investigation. Webb is conducting that investigation one planet at a time. Before Webb launched, scientists knew thousands of exoplanets existed. The Kepler Space Telescope, which operated from 2009 to 2018, discovered most of them by watching for the tiny dip in starlight that occurs when a planet crosses in front of its host star. Kepler's data revealed that small, rocky planets are the most common type in the galaxy. They outnumber gas giants by a wide margin. They orbit nearly every kind of star. Many sit in the habitable zone of their host star, where liquid water could theoretically exist. But knowing a planet exists is very different from knowing what it is like. Kepler could measure a planet's size and orbital period. With additional data from ground-based telescopes, scientists could estimate its mass and density. But the atmosphere, the critical ingredient that determines whether a planet could support life, remained invisible. Kepler did not have the instruments to detect exoplanet atmospheres. That job fell to Webb. Webb is now conducting the first systematic study of rocky exoplanet atmospheres in history. Using a technique called transmission spectroscopy, it watches starlight pass through a planet's atmosphere during a transit and measures which wavelengths are absorbed. Each molecule leaves a unique fingerprint. Water absorbs at certain wavelengths, carbon dioxide at others, methane, ammonia, oxygen, each has its own signature. By reading those fingerprints, Webb can determine what the atmosphere is made of. The results so far have been humbling. Several of the most promising targets have turned up airless. The TRAPPIST-1 system, a collection of 7 Earth-sized rocky planets orbiting a small red dwarf, has been a priority target since before Webb launched. Early results suggest that at least 2 of those planets, TRAPPIST-1b and TRAPPIST-1c, likely lack thick atmospheres. The intense radiation from their host star appears to have stripped them bare. More recently, Webb observations of TRAPPIST-1d, one of the planets in the system's habitable zone, showed no evidence of an Earth-like atmosphere. These null results are not failures, they are data. Each airless planet tells scientists something about which conditions allow atmospheres to survive and which do not. The emerging picture suggests that planets orbiting very active red dwarf stars, which make up the majority of stars in the galaxy, may face a harder time holding on to their air. Frequent stellar flares and strong ultraviolet radiation can erode atmospheres over billions of years. But the discovery of a thick atmosphere on the lava world, TOI 561b, showed that some rocky planets can retain gas even under extreme conditions. And the 5 newly confirmed rocky planets discovered around other red dwarf stars in late 2025 include at least one candidate that may retain a volatile, rich atmosphere. The pipeline from discovery to atmospheric characterization is working. It is just slow. The sheer number of candidates guarantees that Webb will find more atmospheres. Some will be airless. Some will be shrouded in clouds. Some will contain molecules that hint at geological activity, volcanic outgassing, or chemical cycles driven by liquid water. And eventually, perhaps, one will contain something that can only be explained by biology. The search is not about finding one special planet. It is about surveying enough planets to understand the full range of what exists. Tens of billions of rocky worlds in one galaxy. Hundreds of billions of galaxies in the observable universe. The numbers are so large that it becomes almost unreasonable to assume Earth is the only one with life. But to put even those numbers in perspective, you need to understand how much universe is actually out there. And one structure in particular shows the scale in a way that challenges everything cosmologists thought they knew. In 2013, astronomers analyzing data from gamma-ray burst observations found something that should not exist. A wall of galaxies so large that it stretches across 10 billion light-years of space. It is called the Hercules Corona Borealis Great Wall, and it is the single largest known structure in the observable universe. To comprehend 10 billion light-years, consider this. Light from one end of this structure would take 10 billion years to reach the other end, traveling at 186,000 miles per second the entire way. The observable universe is 93 billion light-years across. This one structure occupies roughly 7% of that entire diameter. It is not a small feature in a large universe. It is a dominant presence that stretches across a significant fraction of everything we can see. The discovery came from mapping the positions of gamma-ray bursts, the most energetic explosions in the universe. These events occur when massive stars collapse or when compact objects like neutron stars collide. Because gamma-ray bursts are so bright, they can be detected across enormous distances. By plotting where they occurred in three-dimensional space, scientists noticed that bursts in a particular region of the sky were clustered at similar distances, suggesting they were embedded in a single, enormous structure of galaxies. The wall is not a solid object. Like all large-scale structures, it is a concentration of galaxy clusters and filaments, a region where the cosmic web is denser than average. Think of it as a highway interchange where dozens of filaments converge. The galaxies within it are not uniformly distributed. They cluster along threads and at intersections, with voids scattered between them. But the overall density of matter across this 10 billion light-year region is measurably higher than the surrounding universe. This creates a problem. The cosmological principle, one of the foundational assumptions of modern cosmology, states that on sufficiently large scales, the universe should look the same in every direction and from every location. It should be homogeneous and isotropic. Observations have generally supported this idea. When you zoom out far enough, the clumps and voids of the cosmic web smooth out into a uniform distribution. The scale at which this smoothing happens is sometimes called the end of greatness, estimated at around 300 million light-years. The Hercules Corona Borealis Great Wall blows past that limit by a factor of more than 30. A structure this large should not exist if the universe is truly homogeneous at large scales. Its existence raises uncomfortable questions about whether the cosmological principle holds everywhere, or whether the universe has large-scale variations in density that current models do not account for. Some scientists argue that the detection may be a statistical artifact. Gamma-ray bursts are relatively rare events, and mapping three-dimensional structure from them involves significant uncertainties. The apparent wall could be a chance alignment or a product of incomplete sampling. Others point out that similar large structures, like the Sloan Great Wall at 1.4 billion light-years and the huge large quasar group at 4 billion light-years, also push against the expected limits of homogeneity. Webb does not directly observe structures this large, because its field of view is small and its primary strength lies in depth rather than breadth. But Webb's discoveries feed into the broader understanding of how structures at every scale are connected. The same dark matter processes that built the first tiny filaments, Webb detected at 830 million years after the Big Bang eventually evolved into the monstrous walls and voids visible today. The small and the large are different chapters of the same story. Understanding whether the Hercules Corona Borealis Great Wall is real and what it means for the cosmological principle is one of the biggest open questions in modern science. And one of the tools scientists use to study structures at every scale is a trick of gravity that Einstein predicted over a century ago. Space bends, not figuratively, literally. Mass warps the fabric of space and time, and when light travels through warped space, its path curves. A photon that should have traveled in a straight line instead follows the curvature created by a massive object. If the object is heavy enough and positioned just right, it acts like a lens, magnifying, distorting, and sometimes duplicating the image of whatever lies behind it. This is gravitational lensing. Einstein predicted it, astronomers confirmed it, and Webb uses it constantly to see things that would otherwise be invisible. The principle is simple. A massive foreground object, usually a galaxy cluster containing trillions of stars and enormous amounts of dark matter, sits between Webb and a distant background galaxy. The cluster's gravity bends the light from the background galaxy, redirecting it toward Webb. The effect magnifies the distant object, sometimes by a factor of 10, sometimes by a factor of 100. In extreme cases, along what scientists call the critical curve, magnification can reach into the thousands. Without gravitational lensing, many of Webb's most important discoveries would have been impossible. The earliest galaxies are incredibly faint. Their light has traveled for over 13 billion years, stretched and dimmed by the expansion of space. Even Webb's 21-foot mirror and ultra-sensitive instruments cannot always detect them on their own. But when a galaxy cluster happens to sit in the line of sight, acting as a cosmic magnifying glass, those faint galaxies become visible. Lensing does what no amount of engineering can do. It gives Webb a bigger telescope than the one it actually has. Webb's very first image, the one revealed at the White House on July 11, 2022, was a gravitational lensing image. It showed galaxy cluster SMACS 0723, a massive concentration of galaxies roughly 5 billion light-years away. Behind it, thousands of more distant galaxies appeared, their light bent and magnified by the cluster's gravity. Some were stretched into long, thin arcs curving around the cluster's center. Some appeared as multiple images of the same object, light taking different paths around the lens and arriving at Webb from different directions. That single image, covering a patch of sky the size of a grain of sand held at arm's length, contained galaxies from when the universe was less than 1 billion years old. Some had never been seen before by any telescope. In 12.5 hours of exposure time, Webb surpassed what the Hubble Space Telescope had achieved in weeks. Since then, Webb has observed dozens of lensing clusters. One of the most spectacular is El Gordo, a nickname meaning the fat one in Spanish, given because it is the most massive galaxy cluster known at its distance. Behind El Gordo, Webb revealed a gallery of distorted background galaxies. One, nicknamed the Thin One, appears as an impossibly stretched line of light, magnified and elongated by the cluster's gravity. Another, called the fishhook, curves in a bright red arc that traces the shape of the gravitational field. Lensing also allows scientists to map dark matter because the amount of bending depends on the total mass in the lens, including invisible dark matter. Scientists can work backward from the distortion pattern to calculate how dark matter is distributed within the cluster. Each lensing image is simultaneously a portrait of distant galaxies and an X-ray of the dark matter skeleton holding the lens together. The combination of Webb's sensitivity and gravitational lensing has opened a window that will not close. Every new lensing cluster observed adds more galaxies, more data, more constraints on our models. Scientists now routinely plan Webb observations around known lensing clusters, treating them as natural telescopes that extend Webb's reach far beyond its own capabilities. The universe built these lenses billions of years ago. We are only now learning how to use them. And one of those lensing observations produced the single most humbling image in the history of astronomy. Hold a grain of sand at arm's length. The patch of sky it covers is tiny, a fraction of the full sky. You would need millions of grains to tile the entire view from horizon to horizon. Now point Webb's mirror at that tiny patch and let it stare for 12.5 hours. What comes back is an image that changes how you think about existence. Thousands of galaxies, every smudge, every dot, every streak of light in that image is not a star. It is an entire galaxy. Each one contains hundreds of billions of stars. Many of those stars have planets. The image captures objects spanning billions of years of cosmic time, from nearby galaxy clusters to the faintest smears of light from the first billion years after the Big Bang. Webb's first deep field, the image of galaxy cluster SMACS 0723, was the sharpest infrared image of the distant universe ever produced. It surpassed every deep field observation that came before it, including Hubble's famous ultra-deep field, which took weeks of exposure time to compile. Webb did it in half a day, and it was just the beginning. What makes deep field images so powerful is not just their beauty. It is what they represent statistically. If a random patch of sky the size of a grain of sand contains thousands of galaxies, then the entire sky contains hundreds of billions. Multiplied by the hundreds of billions of stars in each galaxy, the total number of stars in the observable universe reaches a number so large it loses all intuitive meaning. Estimates place it somewhere around 200 billion trillion, written out. That is a 2 followed by 23 zeros. Every one of those stars is a potential host for planets. Every planet is a potential host for chemistry, and every instance of chemistry is a roll of the dice for complexity, for structure, for life. The deep field image does not prove that life exists elsewhere, but it makes the alternative, that Earth is the only place in all of that vastness where something is alive, feel deeply improbable. The galaxies in the deep field are not all the same. The nearest ones, members of the foreground cluster, appear as bright, well-defined ellipticals and spirals. Behind them, the gravitationally lensed galaxies appear stretched into arcs and curves. Further still, the most distant objects appear as faint red smudges, their light so old and so stretched that only Webb's infrared instruments can detect them. Some of those red smudges are galaxies from the epoch of reionization, the era when the first stars and galaxies were clearing the hydrogen fog that filled the early universe. By studying the distribution, colors, shapes, and spectra of galaxies across the deep field, scientists can reconstruct the history of cosmic evolution in a single image. The nearest galaxies show the universe as it is today, mature and structured. The mid-distance galaxies show the universe during its most active period of star formation, roughly 8 to 10 billion years ago. The most distant galaxies show the universe in its infancy, still assembling its first structures. The deep field is a time machine, a census, and a map all in one, and every new deep field observation Webb performs adds more galaxies, more data, more constraints on our models. Scientists have already used deep field data to discover galaxies that should not exist at their observed distances, black holes that grew too fast, and chemical enrichment that happened too early. Each anomaly pushes the boundaries of what we understand. Each anomaly is a door waiting to be opened. The deep field is not just a photograph. It is an invitation to rethink everything we thought we knew about how the universe assembled itself from nothing into this. And behind one of those doors, Webb found the most distant stellar explosion ever traced back to its home galaxy. A blast of energy so powerful, it briefly outshone everything else in the universe. In March of 2025, telescopes around the world detected a flash of gamma radiation coming from deep space. Gamma-ray bursts are the most energetic explosions in the known universe. In a fraction of a second, they release more energy than our star will produce in its entire 10 billion year lifetime. They occur when a massive star collapses at the end of its life, or when two dense objects like neutron stars spiral together and merge. The resulting blast sends a jet of radiation screaming across the cosmos at nearly the speed of light. This particular burst was different. It came from extraordinarily far away. Follow-up observations revealed that it originated when the universe was just 730 million years old. That places it in the epoch of reionization, the era when the first generations of stars and galaxies were just beginning to light up the dark. Telescopes around the world scrambled to observe the afterglow as the burst faded. Ground-based observatories tracked the dimming light across multiple wavelengths. But to confirm the host galaxy, to find the actual birthplace of the explosion, required something more sensitive. That is where Webb stepped in. Webb's rapid response capability allowed it to observe the burst's location quickly after the initial detection. Using its infrared instruments, Webb identified the host galaxy, a faint, distant object that would have been invisible to any previous telescope. This was the first time a gamma-ray burst this remote had been conclusively linked to its home galaxy. The confirmation verified the data from ground-based telescopes and established the burst as the most distant stellar explosion ever traced to its source. The host galaxy itself is small and young, consistent with the kind of galaxy expected in the early universe. It is actively forming stars, which is exactly what you need to produce the kind of massive star that can end its life in a gamma-ray burst. The burst likely came from a star that was born, lived, and died within the first few 100 million years of cosmic history. Why does this matter? Because gamma-ray bursts are more than just spectacular fireworks. They are probes of their environment. The spectrum of the afterglow carries information about the gas and dust between the burst and the observer. By studying that spectrum, scientists can learn about the chemical composition and physical conditions of the intergalactic medium at extreme distances. Each burst is a flashlight illuminating the space it travels through. At 730 million years after the Big Bang, the universe was still in the process of reionization. Neutral hydrogen gas filled much of space, absorbing ultraviolet light and making direct observation difficult. A gamma-ray burst punching through that fog leaves fingerprints in the absorption spectrum that reveal how much neutral hydrogen remains, how far reionization has progressed, and what the environment around the first galaxies looks like. Webb's detection also demonstrates something about the life cycle of stars in the early universe. For a gamma-ray burst to occur, a massive star must form, evolve through its fuel stages, and collapse. The fact that this happened within 730 million years confirms that massive stars were already being produced at high rates in the early cosmos. The machinery of stellar birth and death was running at full speed long before the universe reached its first billion years. Each new detection of a distant gamma-ray burst extends the timeline of confirmed stellar activity further back toward the Big Bang. Webb is uniquely positioned to find the host galaxies of these bursts, confirming their distances and placing them in cosmological context. But Webb is not only looking at the distant past. Some of its most stunning observations have been much closer to home. including a view of stellar birth so vivid that it looks like a cosmic fireworks display. In the outer regions of our galaxy, a young star is announcing its arrival. It has not finished forming. It is still pulling gas and dust from the surrounding cloud, growing heavier by the day. But it is already powerful enough to blast superheated jets of gas into space. Twin columns of material screaming outward along the star's rotational axis at hundreds of miles per second. Webb photographed those jets. They stretch 8 light-years from end to end. That is twice the distance from our own star to the nearest neighboring star system. From tip to tip, the jets span a gulf that would take a beam of light 8 years to cross, and they are being fired by a star that has not even finished being born. These structures are called Herbig-Haro objects, named after the astronomers who first classified them. They form when jets from young protostars slam into the surrounding interstellar gas and dust at supersonic speeds. The collision heats the gas to extreme temperatures, causing it to glow in infrared light. Webb's instruments are perfectly tuned to capture this glow, revealing details that visible light telescopes cannot see because the nurseries are buried inside thick clouds of dust that block optical wavelengths. The image Webb produced looks like a cosmic firework, bright knots of superheated gas flare along the length of the jets. Shockwaves ripple outward where the jets plow into surrounding material. The young star at the center is almost invisible, hidden behind its own cocoon of dust and gas. Only in infrared does the full structure emerge, a newborn stellar engine already reshaping the space around it. Star formation is one of the most fundamental processes in the universe. Every star that has ever existed, every planet that orbits one, every atom of carbon in your body was at some point inside a collapsing cloud of gas. Understanding how that collapse happens, how it produces stars of different masses, how those stars interact with their birth environments, is essential to understanding the universe at every scale. Webb has observed nurseries across the Milky Way and in nearby galaxies. One of its most stunning targets is the Sagittarius B2 molecular cloud, the most massive and active star-forming region in our entire galaxy. Located near the center of the Milky Way, this cloud contains enough gas to form millions of stars. Webb's infrared cameras revealed a colorful array of massive young stars, intricate patterns of glowing dust, and structures that trace the magnetic fields threading through the cloud. In another observation, Webb studied a protostar called EC 53 inches, the Serpens Nebula. This young star is still growing, accreting material from its surrounding disk. Webb's mid-infrared instrument detected variations in the star's brightness that traced changes in the rate at which material falls onto its surface. These fluctuations happen over weeks and months, giving scientists a real-time view of the feeding process that builds stars from gas. The observations matter because they connect the small and the large. The same physics that governs the collapse of a single gas cloud governs the formation of galaxies. The same elements forged in previous generations of dying stars become the raw ingredients for new ones. Stellar nurseries are the recycling centers of the cosmos. Old material goes in, new stars come out. And around those new stars, new planets form, completing the cycle. Webb's ability to peer through dust and observe infrared light has transformed our understanding of these nurseries. For the first time, scientists can watch star formation unfold in environments that were previously completely hidden. Every new image adds another piece to the puzzle of how the universe builds its most important objects. But Webb has not limited itself to distant nurseries and ancient galaxies. It has also turned its golden mirror toward one of the most familiar worlds in our own planetary system and found something nobody had ever seen there before. 3 billion miles from Earth, in the cold outer reaches of our planetary system, Neptune drifts in near darkness. It receives roughly 900 times less light than Earth. Its atmosphere is a freezing mix of hydrogen, helium, and methane, with winds that scream at over 1,200 miles per hour, the fastest in the known planetary system. It is a world of superlatives, and until recently, it was a world of secrets. Webb just revealed one of those secrets. For the first time ever, auroras on Neptune have been photographed in infrared light. Auroras are caused by energetic particles, often streaming from our star as part of the solar wind, becoming trapped in a planet's magnetic field. The magnetic field channels these particles toward the poles, where they collide with atoms and molecules in the upper atmosphere. The collisions excite the atoms, causing them to release energy as light. On Earth, this produces the shimmering green and purple curtains of the northern and southern lights. On Jupiter, auroras glow in ultraviolet and X-ray wavelengths. On Neptune, Webb has now captured the infrared glow of this same process. Neptune's magnetic field is unusual, unlike Earth's field, which is roughly aligned with the planet's rotational axis. Neptune's magnetic field is tilted by about 47 degrees and offset from the planet's center. This creates an asymmetric aurora pattern that does not center on the geographic poles. The auroras appear in unexpected locations, tracing the twisted geometry of the magnetic field rather than the neat polar caps seen on Earth or Jupiter. Webb's near-infrared camera detected the emission from excited hydrogen molecules in Neptune's upper atmosphere. The glow is faint, far too faint for ground-based telescopes to detect against the background noise of Earth's own atmosphere. Only a space-based infrared telescope, floating in the cold silence beyond our planet, could pick up the signal. Webb's position 1 million miles from Earth, and its 5-layer thermal shield, which keeps the instruments at nearly negative 370 degrees Fahrenheit, made the observation possible. The detection matters for several reasons. First, it confirms that the solar wind still has measurable effects on planets 3 billion miles away. The particles that drive Neptune's auroras traveled the entire breadth of the inner planetary system before reaching their target. The fact that they still carry enough energy to produce visible auroral emission tells scientists something about the strength and extent of our star's influence. Second, the infrared aurora data will help scientists model Neptune's upper atmosphere and magnetosphere in new detail. Understanding how energy is deposited into the atmosphere, how it heats the upper layers, and how it interacts with Neptune's strange magnetic field geometry will improve models of giant planet magnetospheres in general. Those models apply not only to our own planets, but to exoplanets as well, where similar processes must occur around gas giants orbiting other stars. Third, the observation demonstrates Webb's versatility. It was built to look at the edge of the observable universe, but it is equally capable of revealing new details about worlds in our own cosmic backyard. The same infrared sensitivity that detects the faintest light from the first galaxies can capture the faint shimmer of auroras on a distant planet. Voyager 2 is the only spacecraft that has ever visited Neptune, flying past in 1989. Webb is now providing a level of detail about Neptune's atmosphere and magnetic environment that no mission since has achieved, and it is doing it from 1 million miles away, without burning a single drop of fuel. But Neptune is not the only nearby target that Webb has transformed. It also turned its instruments toward one of the most beautiful and violent objects in the galaxy, and peeled back layers of dust to reveal what lies at the heart of a dying star. When a star like ours reaches the end of its life, it does not explode. It exhales. Over thousands of years, it sheds its outer layers into space, creating an expanding shell of gas and dust that glows in the light of the exposed stellar core. The core, now a white dwarf, is incredibly hot, often over 100,000 degrees Fahrenheit, and its ultraviolet radiation lights up the ejected material like a neon sign. The result is a planetary nebula, one of the most visually stunning phenomena in astronomy. The Butterfly Nebula is one of the most famous. Its official name is NGC 6302, and it sits roughly 3,800 light-years from Earth in the constellation Scorpius. Hubble photographed it years ago, revealing a dramatic shape, 2 enormous lobes of gas stretching outward from a hidden central star. resembling the wings of a butterfly. The image became iconic. Posters, desktop wallpapers, textbook covers. But Hubble could only show part of the story. The central star is buried behind a dense torus of dust, a thick donut of material that encircles the star's equator and blocks visible light from reaching it. The butterfly wings are visible because gas escapes along the poles, above and below the dusty torus, where nothing blocks its path. The lobes glow in visible light. The core remains hidden. Webb changed that. Using its infrared instruments, Webb pierced through the dust and revealed structures at the heart of the nebula that had never been seen before. The dense torus appeared in new detail, showing layers and textures within the dust. Jets of material, launched from the dying star or its immediate environment, became visible for the first time. These jets carved through the surrounding gas, creating shock fronts and intricate patterns that trace the final convulsions of a star in its death throes. The observations revealed that the Butterfly Nebula is far more dynamic than previous images suggested. It is not a static shell of gas drifting outward. It is an active, structured environment where jets, winds, and radiation interact to shape the nebula in real time. The jets punch through the torus, creating channels that direct the flow of gas into the lobes. The torus itself may not be a simple ring, but a complex, layered structure built up over thousands of years of mass loss. One of the most striking findings was the detection of crystalline silicates in the dust around the central star. These are minerals that form at high temperatures and are typically found close to stars. Their presence in the Butterfly Nebula tells scientists about the conditions in the immediate environment of the dying star, where temperatures are high enough to process raw dust into structured crystals. The star, at the center of the Butterfly Nebula, is one of the hottest known white dwarfs, with a surface temperature estimated at over 400,000 degrees Fahrenheit. It is also one of the most massive known planetary nebula central stars, suggesting that the original star was significantly heavier than ours. Its death was more violent, its mass loss more extreme, and the resulting nebula more energetic and complex than what a lower mass star would produce. Webb's observations of the Butterfly Nebula serve as a preview of our own future. In roughly 5 billion years, our star will exhaust its hydrogen fuel, swell into a red giant, and begin shedding its outer layers. It will not produce something as dramatic as the butterfly, because it lacks the mass, but the basic process will be the same. A slow exhale, a shell of glowing gas, a tiny white dwarf left behind, cooling over trillions of years in the expanding debris of its former self. Every planetary nebula is a memorial, a record of a star that once burned, a system that once existed, scattered into the void, and eventually recycled into new stars and new worlds. Webb is reading those memorials in greater detail than ever before, decoding the final messages of stars that died long ago. And there are still 4 more chapters of this journey left. The universe has more to show you.